Hi everybody, I'm Tao at MC Square of University of Michigan. In this tutorial, I'm going to show you how to get a high resolution STEM image. So I have my sample loaded. Let's check the vacuum. Octagon 7 is good, so let's open the column valve. Okay, now we see the beam is here. Let's go ahead and load a flag register. So I have 300 kV stem aligned. Set. Okay, so next let's find the sample. Um, so since my sample is a fifth sample, I know roughly it should be somewhere around here. And let's start a HDIF live scan. Zoom out to the lowest mag. Move the stage. And now we see the edge of the grid. So let's trace along the grid. Eventually we will find the sample. Okay, looks like we found the sample. And next we do eccentric height. So we do eccentric focus on the right hand panel. And adjust the Z so that our sample will go in focus. Okay, and we see our sample is very bright, so we can adjust the gain so it looks better. Okay, and with this tool we can apply the scan rotation. Okay, and next we're gonna look at our beam, because every time if you load the flag register, highly likely you will have some residual lower order aberrations. The higher order aberrations should be good for over a week, but the lower order aberrations will change day by day. Okay, let's go to an amorphous area and check our beam. So this is a fifth sample, and usually you can use the protective layer on the fifth sample to check the beam. So move an amorphous area to the center. This is the beam park. Just right click the beam park and hit center beam. If you don't do that, you will induce some coma or beam tilts. Okay, let's look at the ronchigram, the flucam, and we see there are lines inside here, and if we change focus and we see the lines change directions by 90 degrees, so that means we have the twofold astigmatism or A1 present. So remember two features for the A1. So one, we have lines, and two, when we change focus, the lines change directions by 90. So we have to fix them. To fix the A1, we can use the stigmator. So we can use probe A1 or condenser to fix the A1. Here the probe A1 is the rough adjustment, and the condenser is more fine adjustment. So let's start with the probe A1 and use our multifunction knob to adjust it. So our beam is currently too strong. We keep burning the holes on the amorphous area, so let's decrease the beam current. Okay, let's go to the stickmeter and use probe A1 to adjust the condenser astigmatism. So now we see the lines are finer and the sample just went away from the screen. That means this direction is wrong. So I'm adjusting the multifunction X, and I'm going to the opposite direction. Okay. And now we see the line started to change directions. That means we'll have to use the other knob, which is a multifunction of Y. And now we see the lines go away from us. Now go to the other direction while we see the lines are going closer to us. And now it started to rotate. We use the other knob. And now I feel I need to make some fine adjustment. Now I change to condenser and try to adjust it. So now I see my ronchogram is kind of symmetric. I don't see obvious lines when I go in and out focus. Maybe just a little bit. Fine tune here. Okay. Okay, so now I don't see obvious lines here, and it looks very contrastless. So that means our beam right now is good. So let's close the stickmeter. Come back to our sample. Let's start scanning. Okay. So let's do one more thing. Let's move away from the sample. Stop scan. Come back to the screen. So right now we are using the 70 micrometer aperture, which gives us 30 millirads of convergence angle. I just found on this TEM it's easier to get better high resolution if we decrease the convergence angle a little bit. So I'd like to change my condenser aperture to 50. To do that, we'll need to draw a circle on the screen. So mark the position of the current 70 aperture, and now go to aperture condenser tool and change it to 50. And now we have to align the aperture to the circle we have drawn. So use adjust, align it to the center of the circle. So with 50 micrometer aperture, we have a convergence angle of 21.4 millirad, which should be good for most of the applications. So now we don't need a circle, delete it. Come back to the sample. Okay. So my sample is gallium nitride film grown on a substrate. I would like to find a thinner area so we get better high resolution. So let's try this area. Now use this beam park, put our beam on the region of interest, and let's look at the FluCam. So this is the Kikuchi map, and here is the zone axis. So we want to align the sample to the zone axis with alpha and beta tilt. So basically we want to this um, move this point to the center of the beam using the tilt. So do a little bit alpha tilt here to bring it down, and we need to do a little bit beta tilt to move it to the left. And when you do beta tilt, your sample will move. It's easier to turn on the sample live view and tilt it while you can see the sample. And every time you tilt beta, you have to fix the eccentric height. So let's double check. Okay, so now see, we're close. Maybe need just a little bit more. Okay, very close. Just a little bit. Okay, so now we see our seabed is very symmetric. That means we are on the zone axis. So next, we just turn on the live scan and zoom in. So zoom into a higher mag, like 3.6 mx, and turn on this reduced area and try to focus. So we should be able to see the high res like this. So as you can see, now the atoms appear very clear already. Sometimes you need to fine-tune your astigmatism here to make the atoms sharp. Alternatively, you can also use the stem auto-tuning. To use stem auto-tuning, you have to stop the live scan and go back to the stem auto-tuning tab and hit C1A1. So by doing this, the stem auto-tuning will find the optimum C1 and A1 value for you. So it says succeeded. Let's go back to this sample and we see the atoms are sharp. So the stem auto-tuning also allows you to tune the A2 and the B2, which is very helpful. To use this function, you will have to first get on a lattice and focus it, and make sure you have uniform lattice in the field of view. And then let's stop the scanning, go back to stem auto tuning and hit the A2B2 button. This will take a slightly longer time, and the software will try to optimize the A2 and the B2, and at the end it will also optimize the C1, A1 for you. So I wanted to comment here, the stem auto tuning function is usually reliable on bulk materials in which you can have clear lattice in the entire field of view. It may not be reliable on nanoparticle samples, and also if your sample is contaminating, you may not get the best result. So now it said succeeded. Let's go back to our sample, start a scan, and we see clear lattice. We can turn on this reduced area and fine-tune the focus, and basically now the focus is already very good. And now we can click this camera icon to take an image. So now we have obtained a high resolution HDIF image. If you want to use other detectors, you can just click the detectors you want. For example, we want to get bright field, so we click BFS, and also let's try ABF and low angle annular dark field. So now we have 4 live scans. These 3 detectors are below the screen, so we'll have to retract the screen. So click R1 button. Okay, so now you see we have 4 detectors scanning lively. We can open the reduced area and try to focus. So now we got 4 high resolution images. This one's HDIF, this one's bright field, this one's ABF, and this one is a kind of low angle annular dark field. So see this ABF images. Um, on each dark dot, there is a small tail. Actually, that is the um, nitrogen columns, and you can see that tail is missing in the HDIF images. Um, so we know that ABF is sensitive to the light elements, while HDIF cannot image the light elements if you have heavy elements at the same time. So this is how you get a high resolution STEM image on the Spectra 300. If you have any questions or comments, please leave a message under this video, or if you are an MC Square user, please send me an email. Thank you. See you later.